So we're getting closer to the end, huh? Always feels like at this time, this part of the semester, you know, I've got these chapters due, and we just feel like we're just trying to pack everything in at the end. We've got like a million more reactions that we want to learn, right? No, not really. All right, so we are ready to start into chapter 24. And like I mentioned, chapter 24 is kind of the culmination of all of the carbonyl chemistry that we've learned so far. So we'll run through kind of a review of all that chemistry in just a minute and show how the new chemistry relates to what we've learned already. Just other announcements, things are ongoing. Remember that we do have an SI tonight. All right, so go to the SI, get more practice on all of these reactions that we've been doing. I know they kind of keep building up. All right, all of the reactions in this chapter, I don't have a clicker today, kind of have name reactions. And so my chapter goals, I think I started getting worn out, and I wasn't very imaginative here. And so every one of them essentially is kind of a repeat of the same, that we want to be able to predict the products and write the mechanisms for a certain reaction. All right? So the first reaction we're going to learn is called the Aldol reaction. Then we got the Claisen reaction, then we got the Michael reaction, and then we got the Robinson annulation. And so these are all the people that discovered a reaction that was good enough to get it named after them. And so we're going to start, well, let's just put this all in perspective. All right, so this is a slide essentially that I think I changed the headline, but that we did earlier on. And so the first type of reactivity that we learned for carbonyl groups, other than just carboxylic acids, the acid-base chemistry, was for them to act as electrophiles, right? And so we looked at reactions where the nucleophile would attack the carbonyl carbon because it has a delta plus at that position. And then depending upon whether this other group here that I have listed as Z, depending on whether that group could behave as a leaving group or not, dictated whether we got a substitution reaction or an addition reaction. So in the top case up here, if Z is a leaving group, so these are essentially all of the carboxylic acid derivatives, acid chlorides, anhydrides, esters, amides, all of these kind of carbonyl groups. If that can behave as a leaving group, then the nucleophile substituted for the Z group, and we got an addition reaction. No, that's substitution. Good. Somebody was awake. We got a substitute. The nucleophile substituted for the Z group, so then we got an addition. Yeah, substitution. Whatever that is. This is a substitution. Okay. If that Z group cannot behave as a leaving group, so essentially if Z is equal H or alkyl, all right, so aldehydes and ketones, then the nucleophile adds, but because we have no leaving group, nothing else can happen, so we just add water, we protonate, and we end up with an addition reaction, right? So an addition reaction, just like you learned for addition reactions to alkenes, right? We added some nucleophile to one carbon, we added an H to the other side. All right? So this was the first thing we learned, carbonyls as electrophiles. In the last class, maybe just the last chapter, we also learned that carbonyl groups can function as nucleophiles. All right? And so in these cases, we generally deprotonated the alpha position to form an enolate, though we saw some early chemistry where we could do the reaction through an enol. But in these cases, in each of these cases, the alpha position ends up acting as a nucleophile. And so we looked at the halogenation reaction, right? If we do the halogenation reaction under basic conditions, then we found that essentially all of the alpha positions would be substituted, okay? If we did it under acidic conditions, one hydrogen would be substituted and the reaction would stop at that point. All right, so we've see how that alpha position can be a nucleophile using a halogen. We also did the alkylation reaction where we use usually a pretty strong base, LDA as an example. We form the enolate and then we use an alkyl halide to just do an SN2 substitution with the enolate being the nucleophile. So we just put a new alkyl group at that alpha position. Okay? So what we're going to do now is essentially look at reactions where the carbonyl group is playing both roles. Okay? So it's like in a movie where the same actor plays more than one part. All right, so let's take a look at the possible outcomes here then. All right, so here we have an enolate. So the enolate is acting as our nucleophile. We have this other carbonyl, and we'll see that in our first examples, two of these will essentially be the same, but they don't have to be. So this side is going to be our electrophile. Just like the reactions we did on the other chapter, the first step is the nucleophile adds to the carbonyl carbon. The electrons go up on the oxygen. And now the outcome, just like we saw before, depends upon whether the Z group is a leaving group or not. Okay? If, let's do it up here, let's say that the Z group is not a leaving group, so it's hydrogen or carbon, so we have a ketone or an aldehyde, then we would, after the reaction is done, we'll add water or dilute acid, and we will get an addition product. All right, so we formed this bond right here. Okay, just like what we saw on the previous slide, but our nucleophiles and enolate. Okay. If, alternatively, that Z group can be a leaving group. All right, and we're going to predominantly look at esters for this reaction, okay? Then we can, in the end, get plus, I'll put plus Z minus over here, we would get a substitution reaction. Okay? So these are both just like what we just saw. The only difference is that we're using an enolate as the nucleophile. Okay? And the carbonyl is the electrophile. Okay, so we're just combining those two. Questions? The first example that we're going to look at is called the Aldol reaction, and I'll tell you why that is in just a minute. Okay, and so all of these, the chapter is called condensation reactions, and so condensations are usually a reaction or kind of a dimerization. We're condensing two of the same molecule. Okay, so let's run through kind of how this would work. Okay, the first step, we have it in basic conditions, and so the first step is going to deprotonate the alpha position. Okay, so this is going to come down here. I'm just going to put the electrons back to the alpha position, and this is really going to form an enolate. Okay, so I'm just going to keep going directly across here. We have one H still there, and we have an enolate. Okay, we know that that enolate, the minus charge, is shared between the alpha position and the oxygen. Right? We have two different resonance forms. In the second step, so we just generated the nucleophile. In the second step, the same aldehyde that has not been deprotonated yet acts as the electrophile. And so just like we showed on the last slide, this enolate can, oh, I didn't want to have an OH there. That should be just an H. What would happen if it was an OH? We would just get acid-base chemistry, right? Okay, so that should just be the aldehyde again. Okay, so this attacks the carbonyl carbon. The electrons go up on the oxygen. We form a tetrahedral intermediate, just like we've seen probably just about 1,000,000 times by now. Okay, so there's our H still there. We've formed a bond here. I'm going to draw it down here. We have the O minus. We have an H. And we have the alkyl group of the aldehyde. Okay, so this is our tetrahedral intermediate. Okay, and the tetrahedral part is right here. Okay, in the last step, once we've done this, we can either just use water, or this can be protonated when we add acid. And let's just, okay, I'll show an H3O plus here. And this can reach over here and protonate. And our product is going to be like this. This comes down here. We have an H and an R group. Here, let me just circle the product since it's kind of running in here. Okay, so here's our product. And so notice what we have if we call this alpha, beta, that's a B, or a beta. This would give us a beta. Dang, this thing is, I think it's starting to fill up or something. It's getting too full up of organic chemistry. Beta hyd. All right, just a minute. Okay, beta hyd. Whoa. Now what's happening? All right, there. Beta hydroxy aldehyde. Okay, so that's the aldol. Aldol. All right, so let's try it again. So look at the next one. Instead of just having an R group, I have an actual side chain. See if you can just draw out what the beta-hydroxyaldehyde product would be for that aldol reaction. All right, so I think the easiest way is if you just draw the aldehyde, the first one, just like we started out with, okay? And then we're going to connect the second one to the alpha position. Okay, the second one is going to go to the second carbonyl, so that's going to turn out to be the tetrahedral atom. Like this. Okay, so in this process we have formed this bond right here. Okay, so some of these aldols, if you keep them in, I think in base still, all of these, so I have this kind of written as an equilibrium here. If the base deprotonates the alcohol, then this can in fact just reverse itself. Okay, so that's just the act of equilibrium. So let's just draw that kind of over this way. So if we used our OH minus again, this would really just be reversing the mechanism that would have got us there in the first place. But this could pull off this proton to make the O minus. Minus our H. And from there, it can just go exactly backwards. These electrons can go down to here to reform the aldehyde. This bond can break, and it goes back to the enolate. Okay, so this process here we usually call the aldol. This process over here we call the retroaldol. Okay, so that's the reverse reaction. Okay. All right, so the bottom example is of a ketone. So the aldol reaction can also be used with ketones. And notice that in my examples here, every time I have written out that 2 of these are going to condense. All right? But I'm not necessarily going to do that when it comes to the exam. Okay? If you see an aldehyde and you see we're just treating it with hydroxide and stuff, you should know, oh, that can condense and do an aldol reaction. Okay? This is too much of a clue.
Too much.
Yeah.
So what prevents it from reversing?
Nothing. Okay, so in general, these reactions, oftentimes, at least what the book says, is that if we do the aldol reaction with aldehydes, the reaction favors the product. Okay? I think just because we haven't created, we've traded sigma bonds for pi bonds, right? Sigma bonds are stronger than pi bonds. And because the aldehyde is very sterically unhindered, it can easily, doesn't get too sterically crowded. However, if we do this reaction with a ketone, the equilibrium lies back towards the reactants because that's more sterically crowded. Okay, so let's draw out how we would do this for a ketone example. So I'm just going to do the same thing. I'm going to draw one of the reactants just as it is. And then I'm going to connect another molecule of this. So I could just go here. Remember, it's going to go to the carbonyl carbon. And so I'm going to have both of those alkyl groups and an OH. Okay? So in this case, we've formed a tertiary alcohol rather than a secondary alcohol. So it's more sterically crowded. And so the equilibrium oftentimes on the ketones lies back towards the reactants. Okay, so there may be other tricks that we can use to drive it one way or the other. Yeah?
Just a quick question. So we saw that with our bromination, this also occurred under basic conditions.
Mm-hmm.
Reversibility, this retro-Aldol mechanism, is this why we don't really worry about disimpeding reaction during bromination or halogenation? Or is there a competing reaction?
I'm sure there, well, this is not so much a competing reaction, right? This is just forward and backwards of the same reaction.
Sorry, competing with so when we talked about carbonyls as nucleophiles,
Mm-hmm.
we could halogenate that. We could also do that halogenation under basic conditions.
Right.
Would this be a competing reaction because it's the same conditions?
Oh, under basic, I see. So the question is, if we're going to deprotonate this from an enolate, and it can condense to do an aldol reaction, what if we just mix into that reaction bromine, right? Is it going to do an aldol reaction faster or slower than the bromination reaction, right? Because essentially we would have two competing reactions. I would say, based upon the results that are shown in the book and other places, that the bromination, bromine itself, must be a kind of a hotter electrophile, and so it reacts with that enolate faster than we see the aldol condensation. It's just, I'm just saying the empirical result, right, of...
So in general, we're not going to worry about a bunch of this contaminant in a bromination.
Correct. We're not going to worry about this. If you see Br2 and OH minus, we're going to think, oh, that's a bromination reaction, right? Yeah. Good question, though. All right, so these are all reactions where we have two of the same aldehyde or ketone coming together, right? But that's pretty limited. We might want to react two different aldehydes or two different ketones or an aldehyde and a ketone and different ones together. So oh no, I'm not there yet. Sorry. Yeah, question.
So because like with the ketone example, there are 4 protons at an alpha position. Why doesn't this happen 4 times?
Yeah, right. So good question. So this question was, since we have 2 alpha positions, why doesn't it happen 2 or 3 or 4 times? I think it may be just a matter of timing. Maybe if you... Well, and stoichiometry, I don't know. If you beat on it enough, maybe it keeps going. I think from a synthetic point of view, we're going to see some better ways in a minute that gives us better control over the reaction than just mixing these things up with hydroxide. I'm not sure how practical that is from a synthetic point of view. But, that's a good point as well. And there's I can't think of any reason why I couldn't do that. Okay, so once we form the aldol, so here's the aldol. This is the one we just had this middle example on the last slide. If we heat this thing up with base, I guess we said it could do a retroaldehyde, but there's something else that can do it. And the same thing can happen if we heat it up with some acid. What do you think is going to happen if we heat up that product, say, with acid? it's just going to do, right, if we use acid, then it could protonate on the alcohol, making a better leaving group, and it does an elimination or a dehydration reaction. Okay, so this can go to form a double bond here, plus water. Okay? And the double bond is pretty stable because it's conjugated with the carbonyl. So our book usually does it under basic conditions, all right? And I want to show you how this happens. It gives the same product, but the actual order of steps is a little bit different than what we've seen before. All right, so in the first step, the base removes this proton, and it essentially forms an enolate at that position. And it can do that. Normal dehydrations usually can't do this because that position is not stabilized by any kind of resonance. The other reason why this can happen is because the leaving group that we have, which is the hydroxide, is not a very good leaving group, right? So we can form this conjugate base. So we form this enolate. And once we have that electron density built up at that position alpha to the aldehyde, that can then be enough to push off the hydroxide. So then these electrons can come down here to form the double bond, and the hydroxide can come off. Okay, and when that happens, we go to the same dehydration product. Okay, so this mechanism, we're just doing a dehydration or an elimination reaction. In the past, we've seen two different mechanisms for elimination reactions, right? We had an E2 where all of the steps happened simultaneously, or it was a concerted reaction. We saw the E1, which had the leaving group come off to form a carbocation, and then we lost the proton. But this one is kind of backwards of that. So we are pulling off the proton to now form an anion that then pushes the leaving group off. Okay, so this has kind of a different name. This is called it does have an E1 because it's unimolecular. Okay, so the rate of the reaction would depend only on I guess the concentration of the reactant, right? Not the hydroxide here, but the reactant. So E1, and then they put a CB, right? And this CB stands for conjugate base. All right, so in this case, the first step goes, it's a two-step reaction. The first step forms a conjugate base, and then we get the elimination reaction. All right? There are other leaving groups that can do this. I don't think our textbook does it. If you have an alkyl fluoride, it can do the same kind of reaction because fluoride is not a very good leaving group, and so in order to do an elimination, you have to be able to pull off the proton to form basically a carbanion to then push the leaving group off. Okay, so this is just a little bit different. I think what's hard to tell exactly is when your aldol reaction is going to go on and dehydrate. Right, so our book kind of says, well, if the side chain has a benzene ring, if you're going to have added conjugation to the new double bond, then it's always going to dehydrate. But other cases, it's kind of harder to say. I think what we're going to do is use kind of a trigger in our reaction here, and we're going to say that if we're adding heat to the reaction, that's going to be enough to drive the reaction forward to do the dehydration. Okay, so if you see what looks like an aldol, but there's no heat, then it will just stop at the beta hydroxyaldehyde. Okay? If there's heat in it, then it will go all the way to the alpha beta unsaturated carbonyl. Okay? Heat drives dehydration. All right, so just so you guys don't have to predict it every time. Okay? So let's just write it over here. No heat. Stop at the aldol product. Heat, dehydrate. Okay, and that will give us the alpha beta unsaturated carbonyl. Okay, does that make sense? All right, so now back to what I was started rambling about. Only doing essentially dimerization reactions is kind of limiting, right? It would be nice to have two different coupling partners, you know, one aldehyde, one ketone, or two different aldehydes. That would really broaden our, you know, the range of our aldol reaction. But let's think about what could happen if we have that reaction at the top there. We have a ketone, and we have an aldehyde. We just mix it all up with base. What are we going to get? A mess, mostly. Is it like an infinite mess, or is it a finite mess? Well, an infinite mess in organic chemistry is usually a black tar in the bottom of your flask. So you could get that. But the point here is that we have two different carbonyls. They both have alpha positions that can be deprotonated to form enolates. They both have carbonyls that can act as electrophiles, right? And so we could essentially couple these in how many different ways? 4 different ways, right? So let's just draw out what the 4 different ways would be. All right, so I'm going to start with the cyclohexanone as the enolate, okay, just for fun. Okay, so in those cases, I'm just going to draw my starting material, and I'm going to connect the other piece to the alpha position, right? So I'm going to connect this to the alpha position. This would be the carbonyl, which is now an alcohol, and this would be one possible aldol product. Okay? The other one, no, I don't think so. Yeah. The other one, where the cyclohexanone could be the enolate, would be the condensation between 2 cyclohexanone rings. Okay, so in this case, we're going to connect here. Here's our OH, and here's the cyclohexane piece. Okay, you might think maybe you would get less of that one. It would be more sterically crowded. We already said that 2 ketones tend to favor more the reactant, but it is a possibility. The other 2 possibilities are if the aldehyde behaves as the enolate, right? And which alpha positions, alpha to an aldehyde or alpha to a ketone, is more acidic? Which one? Next to the aldehyde, right? So that might be easier to deprotonate. It's probably also less crowded. So I might just think that something like this might be our, our biggest product. But that's a possibility. The 4th possibility is the enolate from the aldehyde reacting with the ketone to give us this product. Okay, so this is our mess, right? We could get some big combination of this. So obviously this is not really a very good way to do it, all right, unless you want to make a mess. So another way to do this, what's called the crossed aldol, right? We're crossing between two different molecules, is to do it between two reacting partners where one of them does not have an alpha proton. Okay, so it can only behave as the electrophile. Okay, so here we have cyclohexanone. We deprotonate this. In this case, I'm using a strong base, and we're just using it with benzaldehyde. Benzaldehyde cannot form an enolate, so it can only form as the act as the electrophile, and so we can push this in our favor, right? So the enolate will likely react with the aldehyde. That's going to be the most reactive one. So our aldol product would be like this, but let's put some heat, even though the book says that if we have a system like this with a benzene on there, if we do the dehydration, that double bond will be conjugated both with the carbonyl and the benzene ring, like this, right? So we're still using acid and heat, and we get a dehydration reaction, and we would get something like this. Okay, and the key thing here is one of this has no alpha H. Okay, so only one of them can form the enolate. All right, here. Okay, the top one, again, cyclohexanone, and then we have this other aldehyde. Again, there's no alpha position next to the aldehyde, and so we can just draw the product. The cyclohexanone has to behave as the enolate, and this can react like this. You know, if we heat it up, then it could dehydrate. Another enolate that we can form, remember, which forms more easily than any of the other ones, is this position that is between two carbonyls. So the beta, well, this is malonic ester, right? So we can use methoxide, we can deprotonate in the middle, that can attack the aldehyde, and so we can do the reaction at that position. Right, and if we just did that, then we would have, here's the piece that came from the benzaldehyde, all right, and likely this is going to, because it has that benzene ring, is going to dehydrate. Let's put our little trigger in here. We're going to heat this. It's like the light switch for us. Heat, click, dehydrate. And so we get here. All right, there's an even better way, though, to do these mixed, these crossed aldols, and that is what, well, I think at this point we'd still have this whole combination here. Yeah. And in this case, what we do is we do use LDA with one of the carbonyls. And so essentially we irreversibly make the enolate, okay? And then we add the aldehyde to that, okay? So the enolate just reacts once, right? And then it stops there. And so this is the best way really to control the reaction. So we form the enolate. And so we're really only forming the enolate in the absence of our electrophile. And we're doing it very fast, and so we get no aldol condensation between molecules of the ketone. Okay? There's no equilibration going on. So we enolate formation, and then we add the aldehyde. Okay? And so in this case, we can go straight to the aldol, like this. Okay, and of course, if we have an unsymmetrically substituted ketone, like at the bottom, if we use LDA, which enolate are we going to form? To the less substituted or more substituted side? The less substituted side, and so that's the side where the aldol reaction will go. We're going to get this only to the less substituted side. So this goes via the kinetic enolate. Okay? Yeah?
On the previous slide, can we dehydrate just with heat, or do we get it back?
Yeah, I think if with the acid and heat, or if you add base and heat, then you could cause it to dehydrate.
Because in the last slide,
All right, let's see what else we've got. We're back to starting. So that is kind of the coverage of the aldol reaction. All right? And so the next one is called the Claisen reaction. And this is a reaction between two esters. Okay? So we'll be forming the enolate from the ester, and then that enolate will attack another ester. Okay? So let's just stop there, though. There's no sense in starting that for today. All right? I know, 4 minutes early. That's like a record. 5.
Question for you. So with the previous question with the kinetic enolate, is there a